We're diving straight into the fascinating world of twins in mythology today. That primal image, two beings so alike yet distinct, it really grabs you.
It really does.
And it gets even more intriguing when you look at figures like Castor and Pollux. I mean, here are two brothers right at the heart of so many ancient stories, but with this incredible fundamental difference between them. One was mortal and one was divine.
Yeah, that contrast is exactly what makes their story so compelling, I think. This deep dive is all about unpacking the layers of myth surrounding them.
Right.
We've gathered classical sources to explore their beginnings, their legendary exploits, and, well, ultimately, their enduring significance in the ancient world.
And there's a lot out there, isn't there?
Oh, absolutely. There's a wealth of material, sometimes contradictory stuff, too. We're aiming to highlight the details that truly illuminate their impact and maybe even surprise you along the way.
Sounds good. So let's start at the very beginning, their birth. It's almost, well, comical how even the ancient writers couldn't quite agree on who their father was.
Yeah, that's true.
Homer, in the earliest accounts, sort of just says, both sons of Tyndareus, the Spartan king. Seems straightforward enough.
It does in that early tradition. But then later accounts, especially from Hesiod and then Pindar, they introduce a really significant twist.
Okay.
They propose that while Castor was indeed the son of Tyndareus, Pollux was actually fathered by Zeus himself.
Okay. The old Zeus intervention.
Exactly. This idea of heteropaternal superfecundation twins with different fathers. It's a fascinating reflection of how these myths developed, became more complex over time. Maybe to explain Pollux's inherent divinity.
One divine dad, one mortal dad.
Right.
That immediately sets up the whole mortality dynamic we'll need to dig into. And wasn't there also this really powerful image of them being born from an egg, along with their sisters, Helen and Clytemnestra?
Oh, absolutely. That's a huge part of it.
Talk about an entrance that sticks in your mind.
For sure. The myth of Leda and the swan, Zeus in disguise, laying eggs from which these iconic figures hatched. It's incredibly potent imagery.
Yeah.
It really reinforces their extraordinary nature, regardless of the specifics of their earthly father. And it's worth noting the various names they were known by, too.
Oy.
Well, Dioscuri, meaning sons of Zeus, became a common way to refer to both of them, even Castor, interestingly.
Huh, okay.
Then you had the simple Gemini, just highlighting their twinship, and the more formal Kindarids, acknowledging Tyndareus.
So different names depending on the angle you're looking from, parentage or just the twin thing.
Exactly. It shows how both their parentage and their shared identity were viewed.
Right. So keeping this mixed parentage in mind, let's tackle the big question. Who lived and who? Well, didn't initially. Because their mortality seems to be another point where the stories kind of shift over time.
That's a crucial aspect, yeah, how their story evolves. In Homer's Iliad, there's actually a bit where Helen looks for her brothers among the Greek forces, and she's told they're already dead and buried back in Sparta.
Oh, wow. So both mortal in that version.
Seems like it. That suggests an early tradition where both were considered, entirely mortal heroes. But then if you look later at the Odyssey, we find them alive, although in this very unique situation, they live on alternate days, thanks to Zeus stepping in.
Alternate days, that's such a vivid picture, like sharing a life across two worlds.
It really is. And it hints at this growing recognition of Pollux's divine nature and, well, a desire to keep the twins connected somehow.
So what prompted that shift? How did Pollux, being Zeus's son, end up in this kind of half-life with his mortal brother?
Well, Pollux's divine parentage inherently gave him immortality. The later and probably more famous story revolves around Castor's death in a fight, which we'll get to.
Okay.
Pollux was understandably devastated. He basically begged Zeus to let them stay together.
And Zeus agreed.
Zeus, recognizing this incredible bond, offered a compromise. They would share immortality, spend one day on Mount Olympus with the gods, the next in Hades, the underworld.
Wow. That's powerful. Brotherly love, literally conquering death.
Exactly. It's central to their enduring appeal, I think.
Yeah.
Really speaks to that ancient Greek ideal of, fraternal loyalty. And of course, this alternating existence is beautifully mirrored in their transformation into the constellation Gemini, up there together in the night sky forever.
From alternating between Olympus and Hades to shining eternally together in the cosmos, what a symbol of their bond.
Definitely.
But they weren't just up there in the stars, were they? They had very real roles, responsibilities down here in the mortal world.
Oh, absolutely. The Dioscuri were deeply involved in human affairs. They were hugely revered as helpers of mankind, especially as patrons of travelers.
Travelers, okay.
Sailors, in particular, really looked to them for protection during dangerous voyages. You know, the phenomenon St. Elmo's fire?
That eerie glow on ships' masts.
Yeah. Well, seeing that during a storm was seen as a really positive sign, like a manifestation of their presence, a promise of their help.
So for ancient sailors, seeing that was like, okay, the Dioscuri are here, we might be all right. Direct divine protection.
Pretty much, yeah, in the midst of danger.
And you mentioned they were also linked with horsemanship and boxing. That's quite a range of skill.
It is. Their skill with horses probably connects back to some older Indo-European traditions of divine horse twins. They were always shown as amazing riders in art.
Right.
And Pollux's legendary boxing skill, famously shown when he beat King Amycus during the Argonaut expedition that cemented their link to athletics and contests.
Ah, the Argonauts. We'll get to that.
Yeah. So basically, people saw them as patrons of athletes. They believed the twins would step in during moments of crisis, for those who honored them in sports or other competitions.
So it highlights that Greek value on physical skill and how the gods might favor certain athletes.
Absolutely. Divine favor could be bestowed on prowess.
Okay, so these weren't just distant gods. They were actively involved. Which brings us to their famous mythological adventures. They were kind of the superheroes of their time, weren't they?
In many ways, yes. You see them in the Caledonian boar hunt alongside other big-name heroes. That alone shows their status.
Right.
And their role as Argonauts, joining Jason's crew on the Argo, is packed with important events.
Like the boxing match you mentioned.
Exactly. Pollux versus the arrogant King Amycus. It's a classic story of skill and courage beating brute force. And also, after the voyage, they helped get revenge for Jason against the treacherous King Peleus. Shows their commitment to justice.
So, good team players, skilled fighters, definitely on the side of right. What other big adventures are they known for? I think I remember something about them rescuing Helen before the whole Trojan War mess.
That's right. Before Paris even showed up, Helen was actually abducted by Theseus.
Theseus, the Minotaur guy.
The very same. Her brothers, Castor and Pollux, being devoted, didn't mess around. They launched an invasion of Attica, rescued Helen, and then, as payback, they abducted Theseus' mother, Aethra, and took her back to Sparta.
Whoa, okay. Didn't hold back.
Not at all. They even put Menestheus, a rival of Theseus, on the Athenian throne. Aethra did eventually get home after Troy fell, thanks to her grandsons.
Wow.
But yeah, this whole episode really highlights their fierce loyalty to family, especially Helen, and their willingness to take pretty decisive, even aggressive action.
Clearly a force to be reckoned with. Now, this is all very action-packed, but their story takes a darker turn, doesn't it? With the Leucipides and their cousins. This is where Castor's mortality really becomes central.
Precisely. This is the big one. Castor and Pollux both wanted to marry Phoebe and Hilaria, the daughters of Leucippus. The Leucipides, as they were known.
Okay.
But, these women were already betrothed to their cousins, Lynceus and Idas.
Cousins of Castor and Pollux.
Yeah, sons of Aphareus, who was Tyndareus' brother. So family feud brewing.
Right. What did Castor and Pollux do?
Well, they ended up abducting the Leucipides and marrying them anyway, which, as you can imagine, didn't exactly smooth things over with Lynceus and Idas.
No, I bet not. A classic family dispute spiraling. So, what happened next? This is where the cattle raid comes in and that weird roasted calf thing.
Yes, exactly. The four cousins went on a cattle raid together in Arcadia, but then they argued about how to split the loot.
Figures.
So Idas, who is known for being pretty sharp, proposed this bizarre challenge. Butcher a calf, and the first pair to finish eating their portion gets to divide the whole herd in two, not four.
Wait, an eating contest for cattle?
Yep. And Idas and Lynceus apparently scarfed theirs down super fast, basically tricking Castor and Pollux out of their fair share.
Huh. You'd think heroes with a divine connection might be smarter than that.
You'd think. But they were outsmarted here, and naturally they weren't happy about it. They vowed revenge.
Okay, so this trickery sets the stage for more trouble, especially with Helen's abduction later.
It does, indirectly. Sometime later, Idas and Lynceus visit Sparta, visit their uncle Tyndareus. He's away, though, so Helen is playing host.
Oh.
And Paris of Troy happens to be a guest at the same time. Meanwhile, Castor and Pollux, maybe still looking for payback over the cattle. They make an excuse to leave the feast, planning to steal their cousin's herd. Then Idas and Lynceus leave, too.
leaving Helen alone with Paris.
Exactly, which, as we all know, leads to her abduction and eventually the Trojan War. So in a twisted way, the Dioscuri's feud with their cousins helped create the situation for the war.
Wow. A stolen herd, bad timing. Boom. Trojan War. Mythology loves its tangled webs.
Doesn't just.
But the central tragedy here is what finally happens between the cousins. It ends badly, right? With death.
Tragically, yes. Castor and Pollux eventually confronted Idas and Lynceus. During the fight, Lynceus, who was famous for having incredibly sharp eyesight, spotted Castor hiding.
Oh, no.
Idas then ambushed Castor and fatally wounded him with a spear, but Castor managed to warn Pollux just before he died.
And
Pollux, furious and grieving, went after Lynceus and killed him. Then, just as Idas was about to kill Pollux,
Zeus again.
A thunderbolt took Idas out, saving his divine son.
Lightning from the big guy definitely settles it. But this leaves Pollux alive, immortal, and his mortal twin brother dead.
Yeah.
And this is where that incredible act of brotherly love comes in, the sharing of immortality we talked about earlier.
Exactly. Faced with losing Castor forever, Pollux was given that choice by Zeus.
Yeah.
Eternal bliss on Olympus alone, or somehow sharing his divinity.
And he chose his brother.
Without hesitation, he chose to share, which led to that alternating existence, Olympus one day, Hades the next, a powerful testament to their bond.
It's amazing.
And as we said, it's immortalized in the constellation Gemini. It's also significant, I think, that they were initiated into the Eleusinian mysteries.
The rites about death and rebirth.
Exactly. Underscores the whole theme of their mortality and immortality. And some traditions even say Poseidon, god of the sea, gave them special horses and the power to help shipwrecked sailors, linking back to their role as protectors.
It's such a resonant story, that diversion, and clearly it hit home in the ancient world, given how often you see them in art. Let's talk iconography. How are they usually shown?
Very consistently, actually. Across sculptures, vase paintings, you name it. They're almost always shown as young, athletic guys.
Okay.
Helmeted horsemen, usually carrying spears. Really emphasizes their warrior side and that horse connection. There's even an old manuscript describing them hunting, both on horseback and on foot. Shows their all-around hero skills.
Helmeted, speared horsemen action heroes, like I said. What about other symbols? You mentioned Dokana before.
Ah, yes, the Dokana. That's a key symbol, directly representing their twin ship. It looks like two upright wooden beams connected by cross beams.
Visually showing their connection.
Exactly, an inseparable link. Beyond that, you often see pairs of things with them. Amphorae, those are old storage jars. Free shields, even snakes sometimes, all reinforcing that dual nature. And they often wear these distinctive felt caps called pilos.
The caps, right. Sometimes with stars.
Sometimes with stars above them, yeah. And this is often linked back to the myth of being born from an egg. The rounded pilos is thought to maybe represent the halves of the eggshell.
Ah, clever. So the hats are a constant visual reminder of their weird birth story.
Pretty much.
And you mentioned melodras from Delphi. Those are like carved panels on temples, right? What do they show?
Yeah, exactly. The melotubes from Delphi, these sculpted panels, show key scenes from their myths. Specifically, you see them on the voyage of the Argo, and another one showing them rustling cattle with Idas and Lynceus. So, the big adventures.
So these carvings help tell the stories to everyone.
Definitely. Offers great insight into how the myths were shared. And it's interesting, we also have a written description of what they look like from Darius Phrygius.
Oh, really? What did he say?
Describes them as blonde-haired, big eyes, fair skin, well-built, gives you a clearer picture of how people imagined them.
From stone carvings to detailed descriptions, they were clearly a big deal. Which is reflected in all the shrines and religious rites for them, right? People actively worshipped them.
Oh, absolutely. The Dioscuries were widely worshipped by both Greeks and Romans. They had major temples like the Anikian in Athens and a really important one right in the Roman Forum, plus loads of smaller shrines everywhere.
It's especially important in Sparta.
Hugely important in Sparta. They were linked to Sparta's unique setup with two kings.
The dual kingship, right.
Yeah, and that Dokana symbol we mentioned, they actually carried it in front of the Spartan army like a protective banner. Some people even think the whole two-king system was inspired by the divine twins.
Wow.
Their main shrine, her shrine that's a shrine for a hero, was near Sparta, at Therapne, called the Menelaean. Tradition said Helen, Menelaus, and the twins were buried there. Castor also had his own following up north in Greece.
So both powerful gods and local heroes with strong ties. What kinds of rituals did people do for them?
Well, they got honored in ways fitting both gods on Olympus' big sacrifices and as dead heroes down in Hades, which meant pouring libations like wine offerings.
Covering both bases.
Exactly. Lots of little shrines to them, and Helen dotted the Spartan landscape. The pear tree was sacred to them in Sparta. People would hang little images of the twins and the branches as offerings.
A sacred pear tree.
Yeah. And the standard Spartan oath was by the two gods. That really shows how central they were.
Definitely.
There was also this specific rite called the oxenia. It means God entertaining.
God entertaining. How does that work?
People would set out tables with food, basically inviting the Dioscuri to join them for a meal. Symbolically, of course, either in private homes or public sanctuaries. It was a more intimate kind of worship. Quite distinct.
Like leaving out cookies for Santa, but for Greek gods.
Sort of. And their frequent depiction as attendants of a goddess suggests links to male initiation societies, maybe tied to the Anatolian great goddess or the gods of Samothrace, shows they were woven into broader religious life. And Athens had its own annual festival for them, the Anikia.
From solemn oaths to sacred trees to leaving out snacks, they were really part of everyday life, and their influence went beyond Greece, didn't it? Their legacy spread.
Oh, definitely. You had a whole city on the Black Sea coast named Dioscurius after them.
Wow.
Even the Greek name for the island of Socotra was Dioscoridou, island of the Dioscuri. And there's a great Roman story explaining the family name Ahenobarbus or Aenobarbus.
Meaning?
Brazen-bearded or bronze-bearded. Legend says the Dioscuri appeared to an ancestor, told him about a big Roman victory.
Okay.
And then, as proof, they stroked his hair and beard, and it miraculously turned reddish bronze.
That's one way to prove you've met a god. A rather unforgettable souvenir.
You wouldn't forget that, no.
And it seems this idea of divine twins wasn't just Greek and Roman.
That's right. You see clear parallels in other Indo-European cultures, suggesting a really old shared heritage, like the Vedic Ashvins in India, the Lithuanian Ivienii, maybe the Germanic Alsis.
So variations on a theme across cultures.
Exactly. And the Etruscans, who were in Italy before Rome really took off, they worshipped them too. Call them Castor and Pollux, sons of Tenia, their version of Zeus. They had their own art and symbols for them.
So the idea was already there in Italy.
Yeah, their reverence spread early in Italy and the Roman Empire, probably through the Greek colonies in the south, Magna Graecia. We found a really old inscription at Lavinium that points to this.
So this archetype really resonated, and in Rome itself, they became super important, especially for the military.
Absolutely. The Temple of Castor and Pollux, the Roman Forum, was built really early in the Republic, right after the legendary Battle of Lake Regillus.
Why then?
Because the story goes that the twins themselves showed up on white horses, fought for Rome, and brought the news of the victory back to the city.
Okay, that would definitely get you a temple.
Right. And because of the horse connection, they were especially popular with the Roman cavalry, the Equidates.
Makes sense.
Their feast day, July 15th, was a huge deal. There was this massive annual parade of thousands of cavalry riders through Rome, even in the Circus Maximus, the chariot racing track.
Yeah.
They used eggs as lap counters. A little nod to their birth from an egg.
Subtle, but it's there.
And it's funny, in the Roman comedies by Plautus, you see this pattern where women tend to swear oaths by Castor and men swear by Pollux.
Really? Gendered swearing. That's fascinating.
Isn't it? So from battlefield miracles to everyday slang and even racetrack counters, they were just woven into Roman life.
And it's amazing how even when Christianity came along, they didn't just disappear.
Indeed. Even after the empire became officially Christian, their worship kind of persisted among the people. Pope Gelasius I, way back in the 5th century AD, complained that people didn't want to give up the cult of castors.
Stubborn followers.
Seems so. In some cases, they seem to have been sort of blended, syncretized. Their images or attributes got subtly absorbed into early Christian art. The church definitely tried to replace them, though.
How so?
Promoting Christian pairs, like Saints Peter and Paul as patrons of travelers instead of the Dioscuri. Or the healing saints, Cosmas and Damian, who were also twins. Some scholars even think there might be hidden links between the Dioscuri and other pairs of early Christian saints.
It's like the archetype was so strong it just found new forms. And you mentioned a theory linking them to the New Testament. That sounds wild.
Yeah, New Testament scholar Dennis MacDonald has this theory. It's quite compelling, actually. He suggests Castor and Pollux might have served as literary models for James and John, the apostles called the Sons of Thunder in the Gospel of Mark.
Sons of Thunder, like Zeus's thunderbolts.
Exactly. He calls it early Christian Dioscurism. That thunder nickname echoes Zeus, Pollux's father. And interestingly, the Acts of the Apostles just casually mentions the Dioscuri as the figurehead on a ship carrying St. Paul.
Just like, oh yeah, the ship had Castor and Pollux on the front. No big deal.
Right. Shows they were still just a recognizable part of the world, even in that new religious context.
From ancient Greek myths to maybe influencing the Bible, their story really does echo through the ages. And those examples you mentioned, Etruscan mirrors, Egyptian carvings, Byzantine cloth, they really show how widespread this idea of divine male twins was wherever Greco-Roman culture touched.
Precisely. Those diverse artifacts are like tangible proof of how appealing and adaptable the Dioscuri archetype was across different times and places.
So as we wrap up this deep dive, it's crystal clear that Castor and Pollux were way more than just another old myth. Their intertwined stories, the shared parentage, the heroic deeds, the dramatic divine intervention, and ultimately that profound bond of brotherhood that even beat death, it left a huge lasting mark.
Indeed. Their unique dual nature, mortal and divine, their big roles as protectors and heroes, and that really powerful, poignant image of their shared destiny. It all fed into their incredible, long-lasting cultural impact.
And it really makes you wonder, what is it about this enduring fascination with twin figures like them? What does their story maybe reveal about how humans grapple with mortality, divinity, and that really unique, often complicated bond between brothers? It's definitely something to think about long after our deep dive-ins. Perhaps you, our listener, might even find echoes of this ancient, powerful myth in the stories and relationships shaping our world today.
Welcome to the Deep Dive. Ever wonder about the light we can't see? Today, we're diving headfirst into the fascinating world of infrared radiation.
That's right. Think of light as, a rainbow, but with colors beyond the red end that our eyes just can't perceive.
Right.
We'll explore what this infrared light truly is, where it fits in the grand scheme of energy, and its surprisingly huge role in our daily lives.
And our guides for this invisible journey, well, it's a collection of insights we've gleaned from the Wikipedia page on infrared.
Yeah.
Our mission is simple. Extract the coolest facts, the most useful knowledge, and maybe even a few things that'll make you say, wait, that's infrared.
It's pretty astonishing how much this unseen energy influences everything around us. Really is.
Okay, let's get straight to it then. What exactly is infrared radiation in, plain terms?
Okay, imagine ripples in a pond. Light and infrared are sort of like these ripples. They're waves of energy. Yeah. Infrared waves are just a bit longer than the waves of red light we can see. They sit on the energy ruler, the electromagnetic spectrum, just after red and before microwaves.
Okay.
So while we can feel it sometimes as heat, we can't actually see it with our eyes.
Invisible heat, that's the common association, isn't it? Is that accurate?
It's a good starting point, yeah. And we'll definitely unpack the heat connection later.
Okay.
But technically, infrared is defined by how long its energy waves are, what we call wavelength. This ranges from about 780 nanometers, just a tiny bit longer than red light, up to a millimeter.
Wow, a millimeter. That's quite a range.
It is. And think of a nanometer as something incredibly tiny, like a billionth of a meter.
Right.
These wavelengths vibrate at frequencies from roughly 430 terahertz down to 300 gigahertz. These are just ways scientists measure how quickly those energy waves oscillate,
So, a pretty wide range of these invisible waves then. And I read somewhere that it kind of blurs into another type of energy.
Exactly. The longer infrared waves, specifically those between about 30 and 100 micrometers, a micrometer being a millionth of a meter, they're increasingly being grouped with terahertz radiation,
Right.
which itself is often considered part of the microwave family. So yeah, the lines can get a little fuzzy depending on which scientific field you're talking about.
Makes sense. Different fields, different definitions sometimes.
Yes.
So like all forms of light and energy, infrared has its own characteristics.
Absolutely. It carries energy and even a tiny bit of momentum, like a gentle push.
Yeah.
And here's a bit of a mind bender. It acts both like a wave as we've been describing, and like a stream of tiny energy packets called photons.
Right, the wave-particle duality thing.
That's the one. It's fundamental to how light works.
Okay, that's getting a little cosmic. Let's bring it back to Earth for a second. Its discovery, that's a neat story, isn't it? About an astronomer and a prism.
It is. Yeah, back in 1800, Sir William Herschel, an astronomer, he was playing around with sunlight. He used a prism to split it into the familiar rainbow of colors. Then, being the curious type, he took a thermometer and measured the temperature of each color.
And what did he find? Were the reds warmer?
Precisely. The temperature went up as he moved the thermometer from violet towards red. But the real surprise, the big discovery, came when he put the thermometer just beyond the red light.
Where he couldn't see anything.
Exactly, in an area where he couldn't see any light at all. But the thermometer still showed a temperature increase.
Wow.
He realized he'd stumbled upon an invisible form of radiation, which he initially called calorific rays.
Calorific rays.
Yeah, essentially heat rays. Later, in the 19th century, it became known as infrared, meaning below red.
That's a fantastic bit of scientific history, just experimenting and boom, invisible light.
All right.
We know what it is, how it was found. Now let's dive into the nature of this invisible energy. I know the sun is a major player here.
Absolutely. More than half, a good 50% plus of the energy that journeys from the sun to Earth actually arrives as infrared radiation.
Over half.
Yeah. And most of that is in the near-infrared part of the spectrum, with wavelengths shorter than about 4 micrometers.
Okay.
When sunlight hits the Earth at sea level, it delivers just over 1 kilowatt of energy per square meter at its peak, and a significant chunk of that punch is infrared.
Wow, so the sun is just blasting us with infrared. What about things around us here on Earth? Do we glow in infrared?
Well, yes, in a way. Anything warmer than absolute zero gives off electromagnetic radiation.
Right.
For everyday objects at room temperature, the majority of that energy is released as infrared, specifically in the mid-infrared range, with wavelengths around 8 to 25 micrometers.
Okay.
This is what we call black body radiation, or thermal radiation, basically. The energy an object emits just because it's its temperature. Interestingly, something like a fire produces way more energy as infrared radiation than it does as visible light. Think about feeling the heat from a bonfire even when you're not directly looking at the flames.
That makes perfect sense. You can feel the heat even if it's smoky or, you're not in direct line of sight.
Exactly. And on a tiny molecular level, infrared radiation interacts with molecules by making them wiggle and rotate more vigorously.
Wiggle?
Yeah, it can excite specific vibrational patterns within a molecule. This is actually the fundamental principle behind infrared spectroscopy.
Ah, the analysis technique.
Right. A technique scientists use to figure out what a material is made of by seeing how it absorbs different infrared wavelengths.
So it's not just about the heat we feel. It's also a key to understanding the very building blocks of matter.
Precisely. Now, as we touched on, the infrared spectrum is quite broad, and scientists have carved it up into different sections for various purposes.
Right.
And there isn't one single universally agreed upon way to do this, which can sometimes seem a bit, well, complicated.
Okay, so it's not like a neatly divided line like the colors of the rainbow then?
Not at all. But there's a commonly used system that splits the IR spectrum into 5 main parts. First, there's the near-infrared, or NIR, sometimes called IRA.
NIR.
This spans from about 0.75 to 1.4 micrometers. This is crucial for fiber optic communication because glass fibers lose very little signal in this range.
Yeah.
Also, those night vision goggles you might have seen, they often work by detecting near-infrared light.
Right, the ones that make everything look green.
Some of them, yeah. And it's also used in a technique called near-infrared spectroscopy to analyze materials.
Got it. Near infrared.
Yeah.
Good for seeing in the dark and super fast internet through glass. What's next?
Next up is the short wavelength infrared, or SWOR, also known as IRB. This goes from 1.4 to 3 micrometers.
Okay.
Water really starts to absorb light pretty strongly in this range, especially around 1450 nanometers. Despite this, it's still a key part of the spectrum for long-distance telecommunications, particularly in the 1530 to 1560 nanometer range, where the atmosphere is relatively kind to these wavelengths.
So even within the world of sending light signals, different infrared wavelengths have different sweet spots, depending on water or the atmosphere.
Exactly. Then we move into the mid-wavelength infrared, or MWIR, sometimes called IRC or even intermediate infrared. IIR.
MWIR. Lots of acronyms.
Tell me about it. This stretches from 3 to 8 micrometers. This band is really important for heat-seeking missiles.
Yes.
There's something called an atmospheric window in the 3 to 5 micrometer part where the air doesn't block these wavelengths too much.
Right.
This allows missiles to lock onto the infrared signature of something hot, like a jet engine. This region is also considered part of the thermal infrared, the wavelengths we associate strongly with heat.
Atmospheric window. That sounds like a crucial concept. So the air is transparent there.
Pretty much, yeah. Think of our atmosphere as having like clear and blurry patches for different types of invisible light. Atmospheric windows are those clear patches where certain infrared wavelengths can pass through relatively unimpeded.
Okay.
These are vital for technologies like satellite imaging and, as we mentioned, heat-seeking technology.
Makes sense. So after MWIR, what comes next?
That's the long wavelength infrared, or LWIR. Also sometimes labeled IRC, confusingly.
Oh.
This covers 8 to 15 micrometers. This is the primary range for thermal imaging.
Okay, so the cameras that see heat.
Exactly. Cameras sensitive to these wavelengths can create images of objects based purely on the heat they radiate without needing any external light. Humans at normal body temperature glow pretty strongly in this part of the spectrum.
Right.
And here's a surprising tidbit. A plastic bag is mostly transparent to long wavelength infrared.
Really?
Yeah, while glass is pretty much opaque. So you could potentially see the heat signature through a plastic bag with the right camera.
That's a wild image, like seeing a ghost through plastic wrap. And finally, the last main category in this common system.
That's the far infrared, or FIR, ranging from 15 all the way out to 1,000 micrometers, or 1 millimeter.
FIR, okay.
This region connects to things like far infrared lasers and is associated with detecting very low temperatures.
Okay, so we have near, short, mid, long, and far infrared. NIR, SWIRE, MFDIR, LWIR, FR. Phew, but you mentioned there are other ways to categorize them. Why all of the different systems?
Good question. It really comes down to application. The way scientists and engineers slice up the infrared spectrum really depends on what they're trying to do.
Ah, practical reason.
Exactly. For example, the International Commission on Illumination, the CIE, and the ISO have their own slightly different classifications based more on, say, human perception or industrial applications.
Okay.
Astronomers have another set of categories tailored to observing different temperature ranges out in space.
Great.
Then you have classifications based on how different types of infrared detectors work best, and even specific systems used in optical communications, which divide the infrared into bands like O, S, C, and L.
Oh, yeah, I've heard of C-band.
Right. The C-band, around 1530 to 1565 nanometers, is the absolute workhorse for long-haul fiber optic networks. It's all about the performance of light sources and optical fibers at those specific wavelengths.
So it's like having different maps for different journeys, depending on whether you're sending data, looking at stars, or building a sensor.
That's a great analogy, yeah.
Now, let's go back to that common idea. Infrared and heat. It's often called heat radiation. But you said that's not quite the whole story.
Not quite, no. The crucial thing to remember is that any form of light or electromagnetic energy will heat up a surface that absorbs it. It's not unique to infrared.
Okay.
Think about how sunlight, which includes visible light and UV, warms the Earth. That absorbed energy is then often re-radiated at longer wavelengths, including infrared.
I see.
Even lasers emitting visible or ultraviolet light can generate a lot of heat when their energy is absorbed. It's about energy absorption and transfer.
So it's more about energy absorption and transfer than infrared being inherently heat.
Exactly. However, objects at typical room temperatures do emit most of their thermal radiation in that 8 to 25 micrometer mid-infrared band. Which is why we often associate it so strongly with heat in our daily experience. But this isn't fundamentally different from, say, a hot light bulb glowing with visible light, or even hotter objects emitting ultraviolet radiation.
Right.
It's all part of the black body radiation spectrum. The range of electromagnetic waves an object emits just based on its temperature. The hotter the object, the shorter the peak wavelength where it emits the most energy. That's Wien's displacement law.
Okay. Hotter things glow at shorter wavelengths. Visible light is shorter than IR. Got it.
Exactly. So heat radiation is a useful but maybe slightly simplified way to think about IR.
Okay. Now, how do different materials interact with infrared? I imagine a black shirt absorbs it differently than a white one or a shiny one.
You're absolutely on the right track. This brings us to the concept of emissivity.
Emissivity, right.
Emissivity is basically a measure of how efficiently a surface radiates thermal energy compared to a perfect black body, which is like an ideal emitter. So two objects at the exact same physical temperature can look very different in an infrared image if they have different emissivities.
How so?
Well, an object with high emissivity, like that black shirt, will radiate more infrared energy and appear warmer or brighter to an IR camera. An object with low emissivity, like a shiny silver surface, might reflect more of the surrounding infrared radiation and actually appear cooler in the image, even if its physical temperature is the same.
Ah, because it's reflecting the cooler surroundings.
Precisely. This is why understanding emissivity is absolutely crucial when you're using infrared cameras for accurate temperature measurements in science or industry. You have to account for it.
That makes sense.
Yeah.
A shiny metal pipe might look colder than it actually is on a thermal camera.
Exactly right. Okay, now let's shift gears a bit and explore the truly mind-boggling range of applications for infrared radiation. There are so many.
I'm all ears. Let's start with something most people have probably heard of, night vision.
Right. Night vision devices often use active near-infrared illumination.
Active,
Yeah.
meaning it sends out IR.
Yeah. The device essentially shines out near infrared light, which is invisible to us, like an invisible flashlight. And then the camera part is sensitive to that reflected IR light, allowing you to see in low light or no light conditions.
Okay.
It's important to distinguish this from thermal imaging, though.
Right, which is passive.
Exactly. Thermal imaging, as we discussed, detects the infrared radiation naturally emitted by objects due to their temperature differences. Night vision with IR illumination is about augmenting the existing scene with invisible light.
Okay, so one actively shines IR and the other passively detects the heat given off.
Got it. What about thermography? We hear about that in everything from home inspections to, like, detecting fever.
Thermography, yeah, or thermal imaging. It uses the infrared radiation emitted by objects to determine their temperature remotely. Thermographic cameras typically detect radiation in the long wavelength infrared range, roughly 9 to 14 micrometers, and create images where different colors usually represent different temperatures. Like those pictures where hot things are red and cold things are blue.
Often, yeah, though the color palettes can vary. Since warmer objects emit more IR radiation in this band, thermography allows you to see temperature variations very clearly.
Right.
Initially, it was mainly used in military and industrial settings, think detecting overheating electrical components or finding insulation problems in buildings.
Yeah, I've seen that for houses.
Exactly. But the technology has become much more affordable and is now used in a much wider range of applications, even in some car safety systems to detect pedestrians at night.
So it's like having eyes that can see heat signatures. Okay, what about hyperspectral imaging? That sounds super advanced.
It is pretty advanced, yeah. Hyperspectral imaging takes it to a whole new level. Instead of just capturing a single intensity value for each pixel in an image across a broad IR band, it captures a continuous spectrum across a wide range of infrared wavelengths, NIR, SWIR, MWIR, LWIR, for every single pixel in the image.
Wow, a whole spectrum per pixel. That must be a ton of data.
Oh, it's a massive amount of data. But it allows for incredibly detailed analysis. In the thermal infrared, for instance, each pixel contains a full LWIR spectrum.
And what does that tell you?
It means you can potentially identify the chemical composition of an object without needing any external light source, just by analyzing its unique infrared fingerprint, how it emits light at different thermal wavelengths.
Oh?
It has applications in fields like biology, mineralogy, defense, agriculture for assessing crop health, all sorts of things.
Wow, so it's like a superpowered camera that can not only see the heat, but also tell you what things are made of just by looking at their invisible glow.
Essentially, yes. Very
Right.
powerful. Then we have other imaging techniques using infrared, maybe simpler ones.
Like infrared photography.
Yeah, infrared photography uses special filters to capture the near-infrared part of the spectrum. Interestingly, many digital cameras actually have built-in infrared blockers to prevent IR from messing up regular photos.
Right, because the sensors can see it.
The sensors are often sensitive to it, yeah. But cheaper cameras often have less effective filters, which can sometimes lead to near-infrared appearing as an odd purplish or reddish color in your pictures, especially near strong IR sources like remotes.
I think I've seen that sometimes.
And we can't forget about T-ray imaging, which uses far infrared or terahertz radiation. This is a trickier area because natural sources of these wavelengths are quite weak, but it's a hot area of research with potential in security screening and maybe examining the internal structure of materials non-destructively.
Okay, from seeing heat to identifying chemicals and even peering inside things, potentially. The applications just keep multiplying. What about tracking? I imagine the military relies heavily on IR for that.
Absolutely. Infrared tracking, or infrared homing, is a key technology in missile guidance systems.
The heat seekers.
Exactly. These heat-seeking missiles passively lock onto the infrared emissions from a target anything that's significantly hotter than its surroundings, like an aircraft engine or even a vehicle or people sometimes. Because these objects generate and retain heat, they stand out very clearly in infrared wavelengths against a cooler background, especially through those atmospheric windows we mentioned.
That's a powerful, albeit maybe a bit unsettling, application. Let's move on to something more benign, perhaps.
Yeah.
Heating. We're seeing more and more infrared saunas these days.
Yes, definitely. Infrared radiation is intentionally used as a heating source in various ways. Infrared saunas use special heaters to directly warm your body using IR waves, penetrating a bit deeper than just hot air.
Okay.
It's also used for really practical applications like de-icing the wings of airplanes quickly and efficiently.
Didn't know that.
Yeah. And in industrial settings, infrared heating is becoming increasingly popular for processes like curing paints and coatings, shaping plastics, welding certain materials, and drying products. It's often a more energy-efficient alternative to traditional convection ovens or contact heating methods because it delivers the heat directly where it's needed.
So it's a more direct and targeted way of delivering heat in many situations. Now, here's a surprising one I came across. Cooling using infrared. How on earth does that work?
Yes. This is a really fascinating and cutting-edge field called passive daytime radiative cooling, or PDRC.
PDRC. Okay.
It takes advantage of the fact that certain long-wavelength infrared radiation, specifically in that 8 to 13 or 15 micrometer atmospheric window we talked about.
The clear patch in the atmosphere.
Exactly. That IR radiation can actually escape directly out into the coldness of deep space, right through our atmosphere.
Wow.
So scientists are designing special surfaces, special materials that are really good at emitting thermal energy in this specific LWIR window, while also being highly reflective to sunlight at shorter wavelengths so they don't heat up from the sun.
Okay, so they dump heat out but don't absorb sunlight.
Precisely. This allows these materials to passively shed heat out into space, and they can potentially reach temperatures below the surrounding air temperature, even under direct sunlight, all without using any electricity.
That sounds almost too good to be true. Cooling things down just by radiating heat away into space.
It's real science with incredible potential. Some researchers have estimated that if we could cover just a small fraction of the Earth's surface, maybe 1 to 2% with these PDRC materials, it could significantly alter the planet's overall energy balance and potentially help counteract global warming by passively reducing the amount of heat trapped near the surface and in our atmosphere.
That's a staggering thought, using invisible light to actively fight climate change. Amazing. From heating saunas to potentially cooling the entire planet, what other everyday uses of infrared might we not even realize?
Well, communications is a big one we often overlook. Short-range wireless data transfer using infrared is very common.
Like TV remotes.
Exactly.
Yeah.
That little dark plastic window on your TV remote, that's usually an infrared LED inside that sends out coded pulses of IR light that your TV's sensor detects.
Okay.
This often uses near-infrared wavelengths below 800 nanometers because standard silicon detectors are very efficient and cheap in this range. A key benefit of IR for these applications is that it generally doesn't pass through walls, right? So your remote in one room won't interfere with devices in another, keeps signals contained.
Right, which can be good.
Yeah. It's also used for free space optical communication with infrared lasers. This can provide incredibly high data speeds, like gigabits per second, as an alternative to laying fiber optic cables, maybe between buildings in dense urban environments.
So the same basic tech in my remote could be scaled up for super fast internet between buildings. That's a cool connection.
It's the same principle, yeah, just much more powerful and directed. And there are even initiatives using IR to transmit audio descriptions of printed signs or exhibits to help people with visual impairments using specialized receivers.
Wow, that's a great accessibility application. What about in the world of scientific analysis? You mentioned infrared spectroscopy earlier.
Right, infrared spectroscopy is a really powerful analytical technique. It's used primarily for identifying molecules by looking at how they vibrate.
The wiggling you mentioned?
Yeah, exactly, the wiggling. Every chemical bond in a molecule vibrates at specific characteristic frequencies. If that vibration causes a change in the molecule's electrical balance, what's called its dipole moment, it can absorb an infrared photon of the exact same frequency.
Okay.
So, by shining infrared light through a sample and very precisely measuring which wavelengths are absorbed, scientists get a unique absorption spectrum, like a fingerprint of the molecule.
Uh-huh.
This fingerprint reveals its structure, the types of bonds it has, and ultimately what it's made of. It's an absolute workhorse technique in chemistry, especially for studying organic compounds and checking purity.
So it's like shining an invisible light to see the invisible movements of molecules and figure out what they are based on that. Fascinating. Any other analytical uses of IR?
Yes, quite a few. In the semiconductor industry, for example, they use infrared reflectance measurements.
Reflectance, bouncing light off.
Yeah, they check the properties of the really thin films of materials used in making computer chips. By analyzing exactly how IR light bounces off the surface, they can determine things like the thickness and the refractive index of these incredibly thin layers, making sure they meet specifications.
Going all the way down to the nanoscale of computer components. What about something we see on the news quite a lot, weather forecasting?
Weather satellites rely heavily on thermal or infrared imaging, absolutely crucial.
How to use it?
They use special sensors to capture IR images in specific wavelength bands, typically around 10 to 12.5 micrometers, which is in that atmospheric window.
Right.
These images allow meteorologists to determine the height and type of clouds. Colder clouds are generally higher up. They can calculate the surface temperatures of land and oceans and track weather patterns day and night, which is a major advantage over visible light imagery that only works during the day.
Of course, yeah.
And by comparing images taken in slightly different infrared channels, they can even detect low clouds and fog, which can sometimes be tricky to spot otherwise, especially at night.
So those swirling storm images we see on the weather report are often based on infrared data showing cloud top temperatures?
Very often, yes, or a combination of visible and IR. What about the bigger picture, though? Our planet's climate.
Right, you mentioned climate change earlier with the cooling materials. How else is IR used?
Well, in climatology, scientists are constantly monitoring the infrared radiation emitted by the Earth and its atmosphere. This helps us understand the planet's overall energy balance, how much energy comes in from the sun versus how much is radiated back out to space.
Okay.
Changes in these IR measurements, especially the outgoing long-wave radiation, provide crucial data for studying long-term climate trends, including the effects of greenhouse gases and global warming.
So they measure the heat leaving the planet.
Essentially, yes. They use instruments called pyrgeometers, often placed at ground stations, to continuously measure the broad range of infrared radiation coming down from the atmosphere or going up from the surface for this very purpose.
So infrared is a key tool in understanding our changing climate. Now, I know astronomers use pretty much all parts of the electromagnetic spectrum. What's the big draw for them with infrared? Why build infrared telescopes?
Oh, infrared astronomy is absolutely vital. It allows us to peer into parts of the universe that are completely hidden from visible light telescopes.
Hidden how?
Well, infrared waves can penetrate through the vast clouds of cosmic dust that obscure many interesting regions of space, like the places where stars and planets are being born.
Ah, so it sees through the dust.
Exactly. Visible light gets scattered or absorbed by that dust, but infrared gets through much better. Also, these cool, dark clouds themselves and the very young stars forming within them before they get hot enough to shine brightly in visible light, they emit strongly in the infrared. Infrared is also much better at detecting cooler objects, like planets orbiting other stars called exoplanets. The star vastly outshines the planet in visible light, but the contrast is much more favorable in the infrared, where the cooler planet emits more of its own thermal radiation.
Makes sense.
And furthermore, light from very distant galaxies gets stretched to longer wavelengths due to the expansion of the universe, a phenomenon called redshift.
Right.
So light that was originally emitted as visible or even ultraviolet light from the early universe reaches us today as infrared light. IR telescopes let us look further back in time.
Wow. Seeing through dust, spotting planets, looking back in time. Powerful stuff. What are the challenges, though?
The biggest challenge for ground-based infrared telescopes is water vapor in our own atmosphere. Water absorbs a lot of infrared radiation.
Ah, the blurry patches.
Exactly. That's why many major infrared observatories are placed on high, dry mountaintops, like Mauna Kea in Hawaii or in the Chilean Andes. Or, even better, they're put into space, like the James Webb Space Telescope, to get above the atmosphere entirely. And the telescopes themselves have to be kept incredibly cold so their own heat doesn't swamp the faint signals from space.
Right, makes sense. Space solves the atmosphere problem. Okay, what about some more everyday, down-to-earth applications? I think I saw something about cleaning. Like scanning photos?
Yes, that's a clever one. Some film and flatbed scanners use an additional infrared channel alongside the visible red, green, and blue channels.
Why?
Well, dust particles and scratches on the surface of a photo or negative tend to block or scatter infrared light differently than the actual photographic dyes do. The IR channel captures this information about the surface imperfections.
Uh-huh.
The scanner software can then use this data from the IR scan to digitally identify and automatically correct or remove the appearance of those dust specks and scratches in the final color image. It's often called digital ICE or a similar name.
That's a really clever way to use an invisible part of the spectrum to fix visible problems in old photos.
Okay, and what about art conservation? That sounds fascinating. Using IR to look at paintings.
Oh, infrared reflectography is an invaluable tool for art conservators and art historians. It's amazing stuff.
How does it work?
They illuminate a painting with near-infrared light and capture the reflections with an IR-sensitive camera. Because different pigments behave differently in the infrared, some become transparent, others stay opaque, they can often see beneath the visible layers of paint in a completely non-destructive way.
See underneath, like what?
Like the artist's original underdrawings or sketches made in charcoal or graphite, which often absorb IR strongly. They can see changes the artist made as they were painting, what are called pentimenti.
Pentimenti.
Yeah. This information is crucial for verifying the authenticity of artworks, understanding an artist's creative process and technique, and assessing the impact of past restorations.
So you can see how they built up the painting. Exactly. And recent advances with scanning techniques and different IR wavelengths are even allowing researchers to sometimes see entire paintings that were later painted over by the artist or someone else. They have found hidden portraits under famous works by artists like Picasso and even revealed details under the Mona Lisa. It's also used to examine ancient documents like the Dead Sea Scrolls, where the ink might have faded in visible light but still shows up in IR.
It's incredible, like having X-ray vision for art and history, unlocking hidden stories within paintings. Now, shifting gears completely again, I was genuinely surprised to learn that even biological systems use infrared. Animals can sense it.
Yes, it's quite remarkable. Many organisms have evolved the ability to sense infrared radiation, usually thermal infrared.
Like snakes.
Exactly. Pit vipers, like rattlesnakes, and some boas and pythons have specialized pit organs, usually between their eyes and nostrils. These are incredibly sensitive thermal receptors that can detect the faint infrared heat emitted by their warm-blooded prey, like mice.
So they can see heat.
Effectively, yes. It allows them to hunt very effectively, even in complete darkness. Vampire bats use similar IR-sensitive pits around their nose to locate blood-rich areas, like veins, on their prey.
Wow. Any others?
Even some insects. Certain types of jewel beetles can detect infrared radiation from forest fires, sometimes from miles away.
Why would they want to find a fire?
They use it to find recently burned trees where they lay their eggs because the wood is easier to bore into and there's less competition.
Nature is amazing.
Isn't it? And surprisingly, there's some evidence that certain fish, like carp and maybe goldfish and tilapia, have some sensitivity to near-infrared light, possibly for detecting food or navigating in murky water where longer wavelengths penetrate better. It's like an invisible sense for many creatures.
An invisible sense indeed.
Oh.
And finally, just briefly, I saw mentions of photobiomodulation and also health hazards.
Right. Photobiomodulation is an area where near-infrared light, often from LEDs or low-level lasers, is used for therapeutic purposes.
Like what?
Research suggests it can help promote the healing of things like mouth ulcers and surface wounds. There's also ongoing research into its potential to aid in the recovery from certain injuries, or even potentially help with central nervous system conditions, though much of that is still experimental.
Interesting. And the hazards?
On the flip side, strong infrared radiation, especially the kind you'd encounter in industrial settings with furnaces, welding, or glass blowing very high temperatures, can be harmful to the eyes.
How so?
It can cause thermal damage to the lens and retina over time. Because it's invisible, you don't get that blink reflex you get with bright, visible light.
So workers in these environments absolutely need to wear specialized IR protective eyewear, like goggles or face shields, to prevent potential cataracts or even blindness.
Right. A good reminder that even though we can't see it, infrared energy is real and can have significant effects on our bodies, both good and bad.
We've covered such an incredible range of applications. It's almost hard to believe it all stems from that invisible light Herschel found. Let's just briefly touch on the key milestones in the scientific history of infrared beyond Herschel's initial discovery. Who else was important?
Well, following Herschel's work in 1800, there are numerous crucial advancements. In 1830, Leopold Nobili invented the first thermopile, which was a much more sensitive infrared detector than Herschel's simple thermometer.
Okay.
Then John Herschel, William's son, actually created the first thermal image, what he called a thermogram, back in 1840 using differential evaporation.
Wow, 1840.
Yeah. Groundbreaking theoretical work came from Gustav Kirchhoff with his black body radiation law in 1860, and then later Max Planck's development of the full black body radiation theory around 1901, which really revolutionized physics and introduced quantum ideas.
Right, Planck's constant and all that.
Exactly. Key inventions include Samuel Pierpont Langley's bolometer in 1878. This device could measure incredibly tiny temperature changes caused by absorbed radiation and pave the way for highly sensitive astronomical detectors. And then, of course, the development of the first practical infrared detectors specifically for military use started happening in the early 20th century, really taking off around World War I and II. The first sort of portable infrared device for military applications appeared around 1945.
Okay.
And jumping way ahead, in a more futuristic vein, back in 2013, researchers conducted this really amazing experiment where they implanted a device in rats' brains that connected an infrared sensor to their tactile cortex.
So the rats could feel infrared.
Essentially, yes. They learned to sense infrared light as if it were touch, effectively giving them a brand new sensory input they don't normally have, a form of sensory augmentation.
From simple thermometers and prisms to neural implants giving rats a new sense, it's been an extraordinary journey of discovery and innovation.
It really has.
So, to bring it all together then, we've really taken a deep dive into the world of infrared radiation today. We've learned it's far more than just heat rays. It's a fundamental part of the electromagnetic spectrum with a truly staggering array of applications.
Yeah, it really is. Everywhere.
From helping us see in the dark and measuring temperatures remotely, to analyzing the very composition of materials, enabling our wireless communications, studying the vastness of the cosmos, looking inside artworks, and even holding the potential to help cool our planet.
Exactly. It's this constantly radiating invisible world all around us, and our understanding and ability to harness its power are just constantly evolving.
And that leaves you, the listener, with a final thought to ponder. Considering this invisible world constantly radiating energy, and the ever-expanding ways we are learning to perceive and utilize it, what other hidden aspects of the electromagnetic spectrum, maybe terahertz, maybe something else, might hold equally surprising and transformative potential just waiting to be discovered?
Good question.
It's definitely something to contemplate long after our deep dive concludes. Thanks for exploring the unseen with us today.
Welcome to the Deep Dive. Today we're really going to explore haiku, that incredibly short but really powerful Japanese poetic form. We've pulled together quite a bit, mainly drawing from a detailed Wikipedia article to, well, get under the skin of this miniature literary world.
Yeah, there's a lot there.
Our mission really is to understand its core parts, trace how it developed over time, and see how it's traveled and changed around the world. We want to give you a solid yet, concise grasp of it all.
Definitely. And maybe the best way in is with Basho's famous Old Pond haiku.
Oh, yeah, the frog one.
Exactly. Old pond frog leaps in water's sound. Simple, evocative. In Japanese, it's furu aikakawazu tobikomo bizu no oto.
Right.
And that original has 17 on 575. The translation gives you the scene. But the Japanese, it has its own rhythm, its own kind of pause built in.
That pause, so we'll get to that.
We will.
Yeah.
But this little poem, it holds so much of what we're going to talk about today.
Okay, so let's tackle this on thing right away, because it's not quite syllables like we think of them in English, is it?
Not exactly, no. That traditional 575 structure, it refers to on. Think of them more like sound units or morai. It's about duration, really.
Can you give an example?
Sure. So the word haibun, we say it in two syllables, right? Haibun.
Yeah.
But in Japanese, it counts as 4 on. Haibun en. Each of those sounds gets a count, even the word on itself.
Let me guess. 2 on.
You got it. O-N-N. It seems subtle, but it really affects the rhythm and the perceived length.
Okay, see, so it's a different way of measuring sound.
It is. And it's interesting how that plays out in translation. The Haiku Society of America actually noted that about 12 English syllables often feel similar in length to 17 Japanese on.
Huh. So maybe that's why English haikus sometimes feel, well, shorter, or poets aim for fewer syllables.
Could be part of it, yeah. An awareness of that durational difference. And it's worth remembering, even the masters weren't completely rigid.
Hmm.
Bash himself sometimes deviated. Yeah, his famous one about the wind of Fuji.
Yeah.
That one's actually got a 6-7-5 on pattern.
Interesting. So flexibility even within the tradition. Now, you mentioned a pause earlier. That brings us to kiraji, the cutting word. Sounds quite dramatic.
It does, doesn't it? But it's a crucial element. The kiraji usually comes at the end of one of the three phrases. It acts a bit like a sorta, a break or a pause in Western poetry.
Okay, so it creates a rhythmic division.
That, but also more. It can juxtapose two different images or ideas, sort of, making you think about how they connect. Or it can give a sense of finality to a phrase. It's about creating a space, a moment for reflection between parts of the poem.
Right, so it's doing structural and conceptual work. The article said English doesn't really have a direct equivalent.
No, not a single word that does the same thing. So in English haiku, you often see punctuation like a dash or maybe line breaks doing that work. Or sometimes the cut is just implied by the grammar or the flow.
Can you show us how it works in Japanese? Like in the frog poem?
Sure. In Old Pond, furu ik ya, that ya, after Egg Pond, is the kireji. It creates a distinct pause,
Right.
separating the stillness of the pond from the sudden action kwazu to bikomu, the frog jumping in.
Okay, I hear it now. That little ya does a lot.
It does. And you see it in his Mount Fuji poem, too. But interestingly, some haiku, even by Bashu's and one by Issa mentioned in the article, don't have an explicit kireji,
So how do they create that separation?
often through structure. You might get a short first phrase, maybe 5 on, set against a longer phrase of 12, uncovering the second and third parts. The contrast in length creates a similar kind of two-part feeling.
Clever. Different ways to achieve that balance. Okay, element number 3, kigo, the seasonal word. This seems more straightforward.
On the surface, yes. It anchors the poem in a specific time of year, but it's richer than just saying summer or winter.
How so?
Well, the kigo usually comes from a saijiki.
Huh.
Think of it like a huge dictionary or almanac of seasonal words and phrases specifically for poets. And these words aren't just labels. They carry layers of cultural meaning, specific images, feelings, even historical associations tied to that season in Japan. It's what some call logopeia. The word itself is dense with associations.
So frog might not just mean frog, it implies spring.
Exactly. Or cherry blossoms, obviously spring. Snow means winter, cicadas means summer, and so on. These words instantly evoke a whole sensory and cultural landscape.
But like kireji, not always required.
Correct. Especially in haiku written outside Japan, or in some modern Japanese free-form haiku, you might not find a traditional kigo. The rules have become more flexible over time and across cultures.
Right. So we've got the building blocks, the on count, the kireji cut, the kigo season word. Now, where did this form actually come from? It started as part of something longer, right?
Yes, exactly. Haiku originated as a hoku, which was the opening 3-line stanza of a longer form of collaborative linked verse called renga, and later renku.
Collaborative, so people wrote it together.
They did. The hoku was the all-important first verse. It set the scene, usually included the season with a kigo, and established the tone for the rest of the poem that followed, written by different poets in turn.
Fascinating. So how did it become a standalone poem?
Well, over time, especially around the 17th century with Bashu, the hoku started to be appreciated on its own merits. Anthologies began, including just the hoku. Bashu himself used them powerfully within his haibun.
Haibun, that's the prose and poetry mix.
That's right. Like in his famous travel diary, Oku no Hosomichi, or Narrow Road to the Interior, he'd write these beautiful prose passages and then punctuate them with a hoku that captured a specific moment or feeling. So the hoku was already gaining independence.
And then someone gave it the name haiku.
Yes, much later, in the late 19th century. That was the poet and critic Masao Kashiki. He formally proposed the term haiku for these independent poems, partly to distinguish them from their role in renku. But now we tend to use haiku retrospectively to refer to any hoku intended as a standalone poem, even Bashu's.
Okay, and Bashu, you keep mentioning him. The article calls him a saint of poetry. That's quite the title. What made him so important?
He really transformed the whole tradition. Before him, the linked verse haikai could often be quite light, witty, almost like a game. Bashu elevated it, particularly the hoku, into a serious art form, infusing it with deep feeling, spiritual depth, and this aesthetic concept of sabi.
Sabi.
It's a complex idea, but it relates to a kind of lonely beauty, an appreciation for imperfection and transience, finding beauty in simplicity and austerity. His poems weren't just observations. They felt like profound glimpses into the nature of existence.
Wow.
His influence was just immense. He gathered many disciples, his school promoted the standalone haiku, and yeah, about a century after his death, he was effectively deified. He set the standard.
Incredible. So after Basho, the form continued to evolve. Who came next?
Buson. Joseph Buson, yes, in the 18th century. He's associated with what's called the Tenmai style. What's really distinctive about Buson is his connection to painting.
Oh, right. He was a painter, too.
A very accomplished one. He's famous for haiga, combining painting and haiku together on a scroll or page. And that visual sense comes through in his poetry. His haiku are often very painterly, focusing on light, color, scene, almost like little verbal sketches. Very sensory.
Visual poetry. And then after Busan, we get Issa. His story sounds quite different, more personal.
Very much so. Kobayashi Issa. His life was marked by a lot of hardship, poverty, family loss, and his haiku reflect that, but also his deep Buddhist faith. There's a real humanism and empathy in his work, often focusing on small creatures, insects, children.
Like the one about the rain?
Yeah, or the one asking the cuckoo how much rain it drank. It's tender, direct, sometimes heartbreaking, sometimes humorous. He brought a different kind of accessibility and emotional directness to the form. It feels less lofty, perhaps, than Basho, more grounded in everyday struggles and affections.
It sounds like he made the form feel very relatable.
I think so, yes. He showed how it could be a vehicle for very personal human feeling.
Okay, so Basho elevates it, Busan brings the painter's eye, Issa adds humanism. And then we get to Masao Ashiki again, the one who named it haiku. He sounds like a real modernizer.
He absolutely was, end of the 19th century. Shiki felt that haiku, or haikai as it was often still called, had become a bit stale, kind of stuck in cliches, what he called tsukinami.
Tsukinami, like commonplace.
Yeah, conventional, predictable. He wanted to revitalize it, and he was influenced by Western culture, particularly realistic painting like plein air painting.
Painting again. Interesting link.
It is. It led him to champion chasse, which means sketching from life. He urged poets to observe the world directly, objectively, and capture those fresh impressions in their haiku.
So less reliance on traditional poetic topics, more on direct observation.
Exactly. He also made a point of formally separating haiku from renku, the linked verse, and downplayed the traditional Buddhist connections that were so strong in Basho. He really pushed for haiku as a modern, independent literary form. And as we said, he popularized the name haiku itself.
A real reformer. Okay, so that covers the key figures in Japan. How did this very Japanese form start to travel west? You mentioned Hendrik Doof very early on.
Right. The Dutchman in Nagasaki around, the early 1800s? His lightning haiku is maybe the earliest Western attempt we know of.
But it didn't catch on immediately.
No, not really. For a long time, Western scholars, when they encountered haiku, often dismissed them. Maybe they seemed too simple or the aesthetic principles weren't understood. It took a while.
Until after World War II, it seems, with R.H. Blythe.
Blythe was absolutely pivotal for the English-speaking world. His big 4-volume work, just called Haiku, starting in 1949, and his later history of haiku. These were incredibly influential.
What did he do? Just translate them?
He did translate, but he also explained the history, the aesthetics, the Zen Buddhist connections, although Shiki might have debated that emphasis later on. Blythe basically provided the context and the tools for Westerners to understand and appreciate haiku. He really opened the door.
So he was the main conduit for English speakers, but it was happening elsewhere too. Italy, you mentioned.
Yes, even earlier, actually. In the 1920s, there was Harukichi Shimoi, a Japanese writer and translator living in Italy.
Okay.
He was friends with major Italian literary figures like Gabriele D'Annunzio and introduced them to haiku. D'Annunzio even experimented with it. Shimoi also introduced Ezra Pound to the form.
Pound. The Imagist poet.
The very same. Though, Pound's famous Metro poem, while clearly inspired by haiku's conciseness and imagery, is maybe more imagist than strictly haiku in spirit, but Shimoi was the connection. He even published a haiku by the feminist poet Yusano Akiko in one of his own novellas.
That's quite a network. Then in the 50s, we get two more key figures in English, Kenneth Yasuda and Harold Henderson. They had different ideas about translation.
They did. Yasuda published the Japanese haiku in 1957. He was quite specific. He argued for disking to 5-7-5 syllables in English, not on.
Ignoring the on difference.
Pretty much, for the sake of a familiar English rhythm. He even suggested using end rhyme sometimes to use English's sonic qualities. And he introduced this influential idea of the haiku moment, that flash of insight or experience that sparks the poem.
Okay. And Henderson?
Harold Henderson's warm. An introduction to haiku came out a year later, 1958. He was more aware of the on-syllable difference in length. While he often used a 5-7-5 structure, he focused more on keeping the order of the images the same as in the Japanese, and he often translated them into rhymed three-line stanzas, like ABA.
So Yasuda focusing on syllable count and maybe rhyme, Henderson on image order, different priorities in bringing it into English.
Exactly. It shows there wasn't one single way it was being interpreted or adapted. It was already diversifying.
And it just kept spreading from there, didn't it?
It really did.
Yeah.
France had Pauly Cruchot introducing it. Rabindranath Tagore encountered it and brought it into Bengali. Chinahai Desai in Gujarat.
South Asia, Poland with Chesiamyos, even politicians, Herman van Rompuy.
Haiku Herman, yes, the former European Council president. It just shows how widely it resonated.
And in English, beyond the translators, we see poets really taking it up, the imagists, like Pound.
Yes, Pound's Metro poem is the classic example of that early influence. And there were early Japanese-American advocates like Yo Noguchi and Sadakichi Hartman promoting it.
But the article highlights Richard Wright, too.
Hugely important. The great African-American novelist. Later in his life, he became fascinated with haiku, studied Blythe and the Japanese masters intensely, and wrote thousands of them.
Thousands.
Apparently so.
Yeah.
His collection, Haiku, This Other World, wasn't published until after his death, but is considered a major work of American haiku.
Wow. And the story repeats in other languages. Italy built on Chimoy's introduction.
Yes, Italy saw more experimentation, futurists liked its brevity, eventually haiku associations were formed, poets like Mario Chini, Andrea Zanzotto.
It took root.
In Spain and Latin America. Similar story. Major Spanish poets like Machado, Lorca, Jimenez experimented with it. It popped up in Catalan avant-garde circles. Then Jose Juan Tablada really popularized it in Mexico. And from there, it influenced others across Latin America. Octavio Paz, Jorge Luis Borges. Big names.
Borges wrote haiku.
He did. It seems its conciseness appealed to many different sensibilities.
And even Southeastern Europe.
Yeah. Introduced in Yugoslavia by Milu Krnjanski, then it developed quite strongly, especially in Croatia and Serbia, with dedicated poets like Dubravko Ivančin and Vladimir Divide, journals, clubs, festivals. A real haiku scene emerged there, too.
It's incredible this tiny form just traveled everywhere.
Right.
The article also mentions some related forms quickly. Haibun, haiga, kuhi.
Right. Haibun, as we said, is that mix of prose and haiku, like Bosch's travel writings.
Okay.
Haiga is the combination of haiku and visual art, like Busson's paintings with his poems.
Got it.
And kuhi are poem monuments, haiku cards on the stones or markers, often in places significant to the poem or poet. A very lasting tribute.
Tangible poetry. Finally, just to round out the picture, besides the big four, Bashu, Busson, Issa, Shiki, any other key historical writers we should know?
Well, from the earlier period, people like Arikita Mortake, Nasawa Bonshu, and the important female poet Chione are often mentioned.
Okay.
And from Shiki's time and later, influential figures include Takahama Kyushi, who was more traditional, and Ogiwara Saizensui, who advocated for free-form haiku. Even the novelist Natsume Soseki wrote haiku. So, yeah, a really rich history.
It really is. So let's try and wrap this up. We've journeyed through haiku's core, that unique uncount, the crucial pause of the kyoji, the evocative seasonal kigo. We followed its path from being the hoku, the start of a longer poem, to becoming its own powerful form, shaped by these incredible masters like Bashu, Busan, Issa, and then defined for the modern era by Shiki.
Right, and then we saw it travel the globe, adapting, changing, inspiring poets in, well, so many different languages and cultures. English, Italian, Spanish, Bengali, the list goes on.
It's quite a story.
It is. And maybe that leaves us with a final thought for you listening. How did this happen? How did such a short, specific form, born in medieval Japan, manage to resonate so deeply and universally?
Yeah, what is it about haiku?
Maybe it's about the power of paying attention. The power of capturing just one small, fleeting moment with clarity. It kind of invites you to look at your own world a bit differently, doesn't it? To find those little haiku moments in your everyday life, if you just pause and, well, really see, what might you notice today?